The universe certainly isn't lacking in spectacle, and frequently its actuality surpasses the best science fiction. What you're looking at right now is blackness. Just a minute here. What you're looking at right now are the motions of individual stars in the very center of the Milky Way galaxy. Now, the motions of stars are governed by forces of gravity, and if you look at these stars here on this plot, you'll notice that they seem to have a common center near the center of the frame. Are you seeing that? If you work out the mass of what that central object is, you come up with a number something like 4 million suns, and this object doesn't shine. You're actually looking into the actual lair of a supermassive black hole. Now, as cool as the idea is to physicists of an object which twists up space and time, this isn't the thing about this object which interests cosmologists. The riddle is that we seem to find them everywhere in the universe. Not only across the universe, but almost every when in the universe. So we find black holes that weigh about 1 billion times the mass of the sun when the universe was only 5% its current age. And this is a riddle. This is a question that the cosmologists wrestle with. How on earth do you build something so big in so short of time? What I'm going to be talking about today is a theory which has been pioneered and developed here at Los Alamos National Laboratory with collaborators around the world, which explores this issue. Sorry. I need more of you here to look at. I just keep looking back here. I'm sorry. Which explores essentially this very issue. Black holes may well have captured public interest, but the exotic story of their origins may very well challenge our imaginations. And to see this, you and I have to go back to a time when the universe was first emerging from cosmic blackness, and when individual stars were coming to life for the very first time. We don't have any telescope images of this period, and that's kind of a crying shame, because this period of the universe was foundational in building all big structures. But we do have computer simulations, and that's what we're going to show you now. These sort of bring this period of the universe, this era of the first stars, to life. What you're looking at right now is the formation of the first stars in the cosmos, as computer simulations predict them. Notice that those stars are forming along strings. Are you seeing that? And that they're collecting in hubs. Those hubs are going to be the very first galaxies in the cosmos. Conditions in the universe during this time were alien compared to conditions in the universe now. And this gave rise to truly gigantic stars, stars that were hundreds of times the mass of the sun, tens of millions of times more luminous. This was the universe's Jurassic period, where it was manufacturing monsters, and it's also the home of the biggest explosions in the cosmos. When stars end their life, particularly massive stars, they go up in large supernova explosions. Here's one such explosion. This is a Type 1a explosion occurring outside of its galaxy here. The thing I want you to notice about this is the relative brightness between the two events. The supernova is on the lower left-hand corner here. This galaxy, which is a collection of about 100 billion stars, is rivaled in brightness by this single supernova event. They're absolutely luminous events. In the early universe, stars would have gone off in even more spectacular fashion than stars do today. Some of these stars would have developed antimatter in their cores, and this would have triggered an instability and explosive nuclear burning. These stars would have gone off in a massive blast of light. And that light is, in principle, traveling through the universe today. It's kind of an interesting thought, right? If you take a flashlight, and you should try this on a clear night sky, you should turn on the flashlight above your head. It's an interesting thought that light is going to keep on going until conceivably it hits something. And it's no different for the light coming from these explosions in the very early universe. This light is still traveling in the cosmos, so if you had a sufficiently sensitive telescope, such as the James Webb Space Telescope pictured here, you could in principle look back in time and see for ourselves with our telescopes the very first cosmic explosions. This would be a landmark achievement in astronomy. This would be the achievement of the decade. But as impressive as that would be, these aren't the crowning events of this period in the universe's history. For that, we have to think bigger. This is a simulation by Jarrett Johnson, who now works here at Los Alamos National Laboratory, and you're seeing the formation of a truly gigantic object in the very early universe. Notice the strands that you saw before, those strands of stars, they're all coming together, and at their center, in that very hot luminous spot you're seeing, In the center of the plot there, the universe is building a star. The star isn't going to weigh 100 suns like some of its neighbors, isn't going to weigh 500 suns like some of its very massive neighbors. This star is going to weigh 25,000 suns. It's a monster. We're no longer in the realm of Twinkle, Twinkle, Little Star anymore, are we? These are the mammoths of the early universe. Creatures of almost legend. It's hard to even call that thing a star. It will have lived a very short life, stars like this will have, and at the end would have collapsed quickly, quietly, instantly, and without struggle to form a supermassive black hole, or something that would grow up one day to be like the supermassive black holes that we observe in galaxies today. But once or twice, maybe among 100,000 such stars, the universe would put on a spectacle such as had not been seen since perhaps the Big Bang itself. The biggest explosions conceivably in the universe. Ken Chen shows us what happens when a star, which enters its life with 55,000 solar masses, you can imagine that type of a star. What happens when that type of star dies? There's a consequence of Einstein's general relativity which takes over and triggers an instability deep inside the star. This leads to explosive burning. This star is well on its way to nuclear explosion. You can see that Ken Chen's, he simulated a quarter of a star here. In the aftermath of this explosion, which will unleash about the equivalent of 10,000 normal supernovae, the universe will be fundamentally altered. And that's something that Lionel scientists here have tried to investigate. What happens when the universe's biggest explosion ripples through its own host galaxy? To investigate that, we have to remember that galaxies, as we know them, really didn't exist in the early cosmos when these stars were around. This beautiful grand design spiral structure that you see right here, this is a small dwarf galaxy, by the way. We see that structure. The universe wasn't old enough to make things like this. Galaxies in the ancient universe looked more like this. Notice that this has the same type of structure that we saw in previous slides, where you have the strings of stars and you have the hub, which constitutes the main galaxy there. These two pictures are approximately to scale to give you an idea of how big the structure is. And to put it in context, the star that's going to be exploding inside of this galaxy is about the size of 1/10,000th of a pixel in the left-hand image here. So it makes you wonder, what's going to take place? When the biggest explosion in the universe goes off, will you see anything on those types of scales? Will you see a flash of light? Will individual filaments, those strings, move a little bit? Los Alamos scientists have gone to work and used the supercomputing facilities here to bring the biggest explosions in the universe to life. So ladies and gentlemen, these are the biggest explosions in the universe. This is what happens when the biggest stars die. Absolutely incredible, isn't it? The entire galaxy dies in this colossal explosion. 10,000 supernovae going off in one place. Absolutely incredible. Not only are these the biggest explosions in the universe outside of the Big Bang itself, these would also have been the brightest explosions, conceivably. And if, even though they're incredibly rare events, if you had a telescope that was sufficiently sensitive, such as the James Webb Space Telescope, which will be launched in 2018, you could actually see the birth pangs of the largest black holes in the universe. These explosions do leave behind black holes that may one day grow up to become like black holes again that we see in our own galaxy. To give you kind of a sense of scale here, look at that. We've just punched a hole directly through that galaxy. Pretty crazy. Absolutely incredible. This gives you a sense of scale for the explosion. You're looking at thermal energy right now of the individual particles. I'm going to overlay the Triangulum galaxy here to give you an idea of how large that explosion actually is and actually engulfs that entire structure. Pretty incredible. As impressive as this event is, this explosion will have a more dramatic effect upon the universe. This explosion and a symphony of other explosions in the early universe are going to see the universe with heavy elements, and that'll ultimately draw the era of the first stars to a close. But it'll bring in a new one that's a little bit closer to home, one with beautiful, swirling, grand design spiral galaxies, ones with planetary systems, and life forms like you and me that can look up at the night sky. and contemplate where a supermassive black hole came from. We've talked a lot today about theory, about what we think we will see when we look back at the universe's earliest ages. And it could be that we will see with our telescopes and with our eyes those things which we currently only see in our computers and with simulation. But whatever we see, I'm certain it'll deepen our sense of mystery, which for beings in a universe filled with spectacle, that's probably the way it should be. Thank you.